Theory seminar series. This week we are pleased to have Abhishek Shetty as our guest speaker. Abhishek is a third year PhD student at UC Berkeley, advised by Nika Hatala. Prior to that, he was a research fellow at Microsoft Research India, and even before that, he was an undergraduate student at Indian Institute of Science. He's interested in understanding the interplay between techniques in theoretical computer science and machine learning. So, welcome Abhishek and all yours.
Uh, Thanks for the introduction. So, happy to be here. And we saw in the introduction, I used to be both from IISc and MSR, so really happy to be here. Okay, so today I'm going to talk about work on matrix discrepancy with and relations to quantum communication complexity. There's joint work with Sam Hopkins and Prasad Raghavendra. Also, feel free to stop me at any time. I think we have plenty of time in the talk, so questions would be great. So we can stop at any moment. If I'm saying something that's unclear or want me to slow down, please stop me. Okay, so let's first look at the probabilistic method. By now, it's like a super ubiquitous technique in TCS and combinatorics. The main idea is that random objects satisfy a lot of desirable properties. Standard objects that you construct using this techniques are ANSI graphs, expanders, and designs. So the workhorse that sort of makes this technique work is firstly concentration of measure. In particular, a standard technique that we use to prove this is the Chernoff part. And then, and then you have the union bound. Okay, so but even though this is very ubiquitous, there are situations in which you can beat the union bound. Here's an example. So let's look at this notion called discrepancy. So you have m sets, subsets of n. The aim is to find a coloring from the base set n to plus minus 1. And the aim is to minimize the discrepancy. So what is the discrepancy? So you're summing the colorings in each set and taking the absolute value and taking the maximum over all the sets. So this quantity is called the discrepancy, and you're trying to minimize this over all colorings. Okay, so this seems like a standard thing you can apply the probabilistic method to, because you can always pick a random coloring. So if you take a random coloring, what happens? If by a sort of standard application of the Chernoff bound and the union bound, you get that the error is grows like square root of n log m. So note that the parameters to sort of keep in mind is n is approximately equal to n. So this gives us a bound of n log n if n equals n. Okay. So one might ask if this is tight or if this can be improved upon. And this really famous theorem in combinatorics called Spencer's 6 standard deviations theorem shows that you can actually find a coloring that is with much less discrepancy. So here again, to understand the parameters a bit more easily, just think of m is approximately equal to n. In this setup, you would get so Spencer's theorem shows you that you can get square root n discrepancy, but random colorings give you square root n log n. So this is a concrete example where the union bound can be beaten. Okay, so let's spend a bit more time trying to understand discrepancy and just look at the theorem a bit more. Okay, so we'll change the notation a little bit, so because this generalizes better to the settings that we are sort of interested in. So let's look at, given a set system, let's look at its incidence matrix. That is the jith entry of the matrix is the tells you whether the element j is in set I. Okay. Now you can, in this notation, you can look at the discrepancy as the infinity norm of the signed sum of the columns of this matrix. Does this make sense? Okay. So, okay, cool. So in this notation, we can rephrase the Spencer's theorem as saying for every infinity norm bounded vectors, there is a coloring such that the infinity norm of the signed sum of these vectors is again bounded by square root of n log m over n. Again, as said before, we're interested in, we're mostly going to be interested in like m is approximately equal to n. So cool. The interesting thing about this, even though initial sort of proofs of this theorem came by the very complicated probabilistic arguments, and they were super non-constructive. Recent work in the past about 10 years shows that you can actually find these signings using polynomial-time algorithms. Furthermore, these algorithms are like really simple. Another interesting fact is that you can show that discrepancy is actually NP hard at a scale slightly smaller than square root n even. So it's actually somewhat interesting how algorithms exist in this setup. Okay.
Okay. Can you give
Yes.
some intuition as to what discrepancy means for these vectors? I get the notation, but does it mean anything? Like, what is that saying? The first line.
Sorry, maybe what you're trying to do is okay. So do you agree that this is the same sort of setup as the previous the earlier set
So
system
see,
notation?
subsets and trying to assign like 0, 1 to the minus 1, 1 to the subsets, minimizing that sum. So is it
So
similar to?
you're not assigning okay. So you're not assigning signs to subsets. You're assigning signs to the base elements. That is your ground set. You're assigning signs to the ground set, and you're summing along the subsets. That is okay.
Right.
So you have your base universe like n. To each element in the universe, you're giving signs. Now you're testing if this is actually like a like equally balanced coloring along like prescribed subsets. And for each one of these subsets, you want the sign to be small. Similarly, here you have vectors that are sort of promised to be small in some sense, in like promised to be L infinity bounded by 1. And you're given these vectors, and you're asked to minimize the sizes of these vectors as much as possible while assigning them signs. Does this make sense? And the way of thinking of this is you're trying to partition your vectors into two sets such that they look as similar to each other as possible in
Yeah.
infinity now.
Yeah. Okay. Thanks.
Does that make sense? Yeah. Again, feel free to. Yeah. Thanks for the question. Feel free to stop me at any point. Cool. So yeah, so that's discrepancy. And turns out studying discrepancy has sort of led to many connections to probability, combinatorics, and convex geometry. It's a whole area by now, and it's has shown like super interesting connections to all these areas. Okay, so what we are interested in today is a potential non-commutative analog of this. So what does that mean? First, before like getting to the non-commutative discrepancy problem, let's look at the origin of this question that we started with, the Chernoff bounds. So it turns out the Chernoff bounds have a non-commutative analog, which is called the matrix Chernoff bound. It has been here's one simple version of the matrix Chernoff bound. So whenever I have matrices and I write norm, I mean the infinity norm unless otherwise, as in the spectral norm unless otherwise specified for matrices. So this is the form of the Chernoff bound. It basically says the largest eigenvalue of a sum of like random matrices has a certain concentration. Again, these bounds by now have become like instrumental and standard techniques in TCS, physics, machine learning, and spectral graph theory. The question now is, can we beat the matrix Chernoff bound and the union bound? Okay, so let's formulate the conjecture. As before, before we had vectors. Now you have matrices in Rm cross M, n matrices in Rm cross N, all of whose spectral norm is bounded by 1. The question is whether there exist signs such that the spectral norm of the sign sum is bounded by square root of n log n log m over n. This is the same bound as the Spencer's setting. Again, it's useful to sort of restrict to the case where m equals n, because it's easier to compare. And one can see that matrix Chernoff plus a union bound gives you a bound of square root n log n. The question now is that can you remove that log n, square root log n, I guess, using other techniques. And this question has been has come up in sort of various different forms and has been open for 10 years, roughly 10 years now. And the study of this has sort of led to a few interesting techniques. So, okay, so one can ask why would you believe such a statement at all? The first sort of interesting case is that when all the AIs commute, one can easily see that this actually reduces to the vector case by taking the matrices to be diagonal matrices with the vectors along the diagonal. Is everyone convinced that that makes sense? Okay. Cool. Another interesting regime is when AIs are very far from commuting. One sort of standard way to enforce that very far from commuting is by taking the matrices to be random. So if AI to AN were sort of random matrices, then you can show using standard random matrix theory, you actually get a bound of square root n, not square root n log n. Actually, sort of more recent works quantify non-commutativity, and you can show that in a certain sense, if you're sufficiently non-commuting, you get recover square root n back. So there's a sense in which when you're super structured algebraically, you satisfy this conjecture. And when you're very far from structured algebraically, we can also satisfy this conjecture. So this sort of tells us that maybe this conjecture is true, or something interesting is happening in between, which is worth studying anyway. So does that make sense?
So can you say a little bit about what highly non-commuting means?
Okay. So one easy model for highly non-commuting is the following: you take arbitrary matrices A1 to AN, and then you hit them with a random unitary. Each one with a random independent unitary. You can show that this system satisfies the conjecture. For example, the other thing that I was talking about recent work by Van Handel et al. That is a bit complicated to explain, and it will take us a bit far afield. Maybe we can talk about it offline. But roughly, there's the structure that they try to capture is basically this: when you hit AI with like sort of random matrix, like it behaves like you were hitting it with random matrices, random unitaries in some sense. Does that make sense?
So, okay, so is it like saying that the singular vectors have to be like very far from each other? Is that what it's trying to capture?
Yeah. So it's sort of like that, but yeah. As in the singular vectors somehow are not. So we can think of the matrices as symmetric actually. So it's essentially without lots of centrality. So let's think of as eigenvectors, and yeah, it's sort of the the algebraic structure of the eigenspaces somehow are don't interact much. That's yeah. Does that make sense?
Okay. And are we assuming the matrices are symmetric or no?
It's essentially without loss of generality, because you can do some Hermitian dilation sort of trick, which is you take your matrices and like set them as block diagonal matrices with like 0, 0, A and minus A transpose. Sorry.
I see. Okay.
So we can think of them as being symmetric or not symmetric. It's not super important. No. So let's actually just think of them as being symmetric. Maybe I should have just written that on the slides.
Hey Abhishek, just one more question. In similar vein to what Anand just asked, what is the measure of non-commutativity? Like when you say highly non-commutative or less non-commutative?
Yeah. So okay. I was trying to avoid this question. Okay. So uh, uh, you can sort of formalize this. There is turns out the covariance matrix of the matrix sort of as a vector somehow works as the measure of like it's a little weird actually. Like so. I don't want to get into it right now, but again, the model that you should again think of is that you take AI and then you hit it with a random unitary map. Each one is a independent random unitary map, and that's sort of a model for being far from non-commuting. The question is how well you approximate that process.
Right. Okay.
This is okay. Since we're talking about this already, so this sort of question about like when do you actually maybe it's too much of a digression. Let's talk about that offline. I'm
Sure.
sorry if I didn't answer the question precisely. Okay, cool. So let's briefly look at what sort of work has been done on this conjecture. One can show that without too much difficulty for like constant rank matrices, random signs work. Furthermore, there's an interesting paper by Levy, Rothos, and Ramdas that show that for block diagonal matrices also things work. And similarly, there's sort of improvement on this by Dadouche, Jiang, and Rees. We'll get back to this paper in a bit. And people also studied related questions. Somehow this is related to, in certain parameter regimes, this is sort of related to the Cadison-Singer problem. So there is some work related to that by Le King Song. Right. Okay. So here's a overview of our results. First, in my opinion, the main thing we show is that we show a new perspective on discrepancy. We show that vector discrepancy, which we saw, Spencer's theorem is somehow related to classical communication. And the main thing we'll talk about most the rest of the talk is matrix discrepancy is related to quantum communication. Using this idea, we show that we can recover the matrix Spencer conjecture for moderate rank matrices. What do I mean by that? So let's say you have matrices A1 to AN in Rm cross n, such that the rank is less than square root n of each of the matrices. And again, we are assuming the spectral norm is bounded by 1. We show that there exists a sign such that the sign sum of the matrices is bounded by square root of n log m over n. Furthermore, we can also show that these signs can be found efficiently in polynomial time. But most of the talk we will not talk about the algorithm itself, but happy to chat about that also offline. Interestingly, in concurrent work, Dadouche, Jiang, and Rees also made some progress on the conjecture. They show several interesting things. The paper is also worth looking at. But unfortunately, in the regime where m is approximately n, they only recover sort of constant rank. Right. Okay. Is the summary of our results clear? Okay. Great. Here's sort of a non sequitur, but it's sort of here just to keep you interested, I guess. Here's a concrete conjecture in quantum communication complexity. Again, if you're not seeing quantum communication complexity, feel free to ignore the slide. But here's in a minute I'll tell you why this is interesting. So there's a standard function in communication complexity called the index function, and here's a conjecture about this. So we are asking for the expected so Alice has a random x, Bob has a worst case y, and we want to understand the one-way communication complexity of the index function, where the success probability is very close to half. So this is half plus c times square root n. And the question is whether for some c, you need to communicate at least log n qubits. Again, it's not super important if you fully understood what this conjecture is, but it's the point is that it's a concrete conjecture about like a super simple function in quantum communication. What we show is that this conjecture implies the matrix Spencer conjecture. Furthermore, we show that a classical version of this theorem, basically you replace qubits with bits, leads to a new proof of the Spencer theorem. So that's somehow with this new connection to communication complexity, we can show that we can recover a new proof of the Spencer theorem using these ideas. Does that make sense? Okay, cool. So the rest of the talk is mostly going to be technical, and we're going to talk about we're going to spend some time talking about communication complexity, motivate why communication might be related to discrepancy, and then see a few results and see where we get from there. So if you have any questions about the conjecture itself and why it's interesting, or anything sort of about the general conjecture, not necessarily this conjecture, even the matrix Spencer conjecture, this would be a good time to ask, because at this, like, from now on, we'll start talking about communication complexity.
So I have a question about this. So would it be fair to call it as a quantum analog of Shannon capacity?
So this is a good question. So we'll see later that somehow, okay, so if the error was, like, say, constant, so instead of like half plus c over square root n, you can prove the corresponding theorem using just sort of general purpose information theoretic techniques. And the quantum version of this you can prove using, again, quantum information theoretic things. Like if you've heard of the Holevo bound, you can prove it using some clever application of the Holevo bound. But somehow at this low error region, information theory does not work. And what I mean, roughly the reason is somehow this is to do with discretization, but also like we'll see more precisely why. Okay, more precisely, it's sort of mathematically why it fails, but like approximately you should think of it as like an issue with discretization, like in some sense. Like, so for example, okay, so if you know the index problem, if the error was constant, you can show that you need like sort of linear number of like one-way communication. So basically, Alice has to send the her whole message. But like when you have such small error, this is not true. When you have such like such a high error, I guess, like small advantage, this is not true. So yeah, maybe it'll become more clear further in the talk. Should I continue?
Yeah, sure.
Okay, great. Cool. So we're just going to spend some time just talking about communication complexity for a few more slides. Okay, so what are we going to be interested in? We're going to be interested in the one-way communication complexity of the index function. So let's look at what that is. So as standard in communication complexity, there's Alice, and then there's Bob. Alice has input, which is a n-bit vector, and Bob has an index from 1 to n. And Alice has to, so we're talking about one-way communication complexity. So Alice has to send a message to Bob. It's called a message M. And the aim is to compute for Bob to output x of I. So this is the function. So for the rest of the talk, it's sort of, it's best to think of Alice and Bob having only private randomness. public randomness makes, at least in the regime we are in, maybe things a little bit weird. Okay. So that's the problem. That's the index function. And the size of the protocol is the number of bits or qubits in M. So if the message is classical, we'll count the number of bits. If the message is quantum somehow, we'll count the number of qubits in M. Does that make sense? This function is in some sense complete for one-way communication, because you should think of Alice as holding a function and Bob is holding input X, and we are evaluating. Bob is asking to evaluate a function on the input. Does that make sense? So this is the index function. This is the communication complexity. This is the one-way communication complexity of the index function. This is the quantity that will be done.
Sorry. Do they communicate beforehand anything? Like, do they share functions and so on? Share the same
so okay. So in standard sort of communication complexity setup, they're allowed to agree on a protocol. However, like they're allowed to agree on an arbitrary protocol beforehand. And in some models of communication complexity, they're also allowed to share randomness. But again, we'll not worry about them sharing randomness. So they're allowed to agree on a protocol. They can do whatever they want beforehand. Then they're somehow separated, and Alice gets X and Bob gets I. Okay, that's the model.
Yeah.
And they can run arbitrary computation. They're not computationally bounded. They can do whatever they want. But the notion of complexity is the number of bits that they send. That's the only bottleneck. Right. Oh, and there is no adversary or anything of the sort. There's Alice and Bob are both honestly running the protocol they agreed on. Does that make sense?
Yes. Thanks.
Okay. Yeah, cool. So this is the communication complexity of cool. So let's see why somehow classical communication is related to the discrepancy. So let's say there are vectors v1 to vn. For now, let's think of them as being in the plus minus 1 to the m. That's say don't have a good signing. That is for every signing x in the hypercube, the sign sum of vi has infinitely non-responded away from delta. Somehow we'll relate this to communication complexity. So let's say such a set of vectors exists. We'll construct a log m plus 1 bit protocol for the index function. So what Alice does is the following. Alice on input x finds index j such that the jth coordinate of the sign sum is larger than delta, and then sends across to Bob j and the sign of that index. Bob on input I, what he does is looks at vi and the jth coordinate and multiplies it with s and outputs this. So this is the protocol. Is the protocol clear? Okay. So this is a sort of simple protocol given such vectors. We'll show that this the norm condition implies that this protocol has non-trivial error guarantees. So the claim is the following. For every input of Alice, Bob has the following success probability. He gets advantage, that is delta over 2 over n above half, but in expectation over xi. So we are thinking of Alice as being worst case. So Alice has worst case inputs x, and Bob has a random index I, and here what we are trying to sort of do is solve the index problem in this regime, and we're showing that if such vectors exist, Bob has the success probability. Does this make sense? Okay. So we'll quickly see why this is implied. This is not super difficult. The proof actually just follows by just writing out writing out the success probability, which is just 1 over n times the sum that it agrees with what Bob is outputting, and by just then noticing that this term is the same as the infinity norm of the vector, because J was chosen such that it is greater than, or at least it's greater than delta over 2. Does that make sense? Or greater than delta, I guess. Does that make sense?
This is a per index guarantee, right? This is a per index guarantee, right? It holds for every I.
No, it holds an expectation over I.
So can we say anything about the entire message?
What do you mean? Anything about the entire message? Per index, as in it holds in per index over like Bob's. It's an expectation of Bob's index I. The message is just the index. Okay, so the message is the index of the code. So, okay, sorry. Okay, maybe we should be careful about what worst case is. Alice's input is worst case. Bob's input is average case, and the message is follows this protocol that we just talked about before. It's not clear to me how. Oh, sorry. Keynote does mysterious things. Sorry. So therefore, the message follows this protocol from before. So message has some distribution. It's unclear what the distribution of the message is, but it basically is like it's the index satisfying, in some sense, index satisfying the infinity norm condition. Does that make sense?
Thank you.
Thanks for the questions. So turns out you can actually go the other way as well. So whenever there's a protocol, you can actually show that there are such vectors satisfying this condition. Basically, you can construct such a matrix by like those vectors matrix by sort of looking at Bob's output, but let's not spend too much time on that. So basically, what we showed is that a log m bit protocol plus 1, I guess, but log m bit protocol such that minimum over x, the expectation of over I, the probability of success is half plus delta over n, is in 1-1 correspondence with vectors on the hypercube, such that the discrepancy is at least greater than delta. And this is a 1-1 correspondence. So basically, discrepancy upper bounds are communication lower bounds. Does this make sense? So far, what we have discussed is somewhat classical. It's I guess folklore in the discrepancy literature, but maybe it's not easy to find this written this way anywhere. But it's somewhat like classical. The point is that somehow discrepancy and communication are in some sense the same thing. Is everyone convinced?
So how do we get an algorithm for discrepancy from this?
Yeah, so from this, it's very far from clear you can do anything actually. It's actually maybe in 2 slides I'll talk about what. So it's not even clear how to prove discrepancy bounds using this, because somehow you have to prove lower bounds in a very strange model, which is worst case Alice, average case Bob. And this model turns out to be very brittle, and it's like a little difficult to show low bound communication low bounds in this setting. So what I've spoken so far is not even clear it's useful for existential results, not let alone algorithms. It's not even clear how to use this at all. We'll get to in a few more slides. We'll get to sort of how to get around this problem, and that's somewhat where our work comes in. Does that make sense? Okay, so we'll quickly see a quantum, just like a one slide, the thing on how quantum mechanics works. It's a way too fast, I guess. But it's not super important if you haven't seen quantum information or anything like that before. We'll use like super simple sort of axiomatic things about quantum mechanics, which you can take sort of as black box things about quantum mechanics. It's nothing super important. Okay, so what we need is the notion of a quantum state. A quantum state is basically a vector. Sorry, it's a oh, sorry, there should be n cross n, I guess. It's a matrix which is PSD and has trace 1. So this is a quantum state or a quantum mixed state. And with a quantum mixed state, what you can do is this thing called a quantum measurement. One way to think of a quantum measurement is you have a tuple of operators such that they're positive and they sum to the identity. And the semantics of this set of operators is that the measurement gives you I with probability that is trace of AI times rho. Does that make sense? Again, it's not super important if all of it did not make sense. We just sort of roughly what you want to sort of keep in mind is that instead of probability distributions, you sort of have PSD matrices with trace 1, and with probability distributions, you take the expectation. Here, the corresponding thing you're doing is sort of taking trace, which is the inner product for matrices, the corresponding inner product for matrices. That's sort of roughly all you need to know. So far, so good. Okay, so now let's look at the same version of the game with quantum communication. So let's say there are matrices A1 to AN, again with spectral norm bounded by 1, and such that for all signings, you have that sigma xi AI is greater than delta. First thing to notice is that this implies by duality that for every x there is a matrix yx, which is PSD and trace 1, such that the trace of y times the sign sum of the matrices is greater than delta. This is nothing about quantum. This just is the duality of the spectral norm. Does this make sense? Is everyone convinced this is true? Another way of thinking of this is that somehow this is the dual program for maximum magnitude. Should I move on? Okay, cool. So what we'll think of as before, what we'll think of this. Okay, maybe before that we'll look at some notation. Let's denote AI plus minus 1 as the same AI but added to half times the identity. It's the half symmetrized versions of AI. And because the spectral norms were bounded by 1, we have that AI plus minus are PSD. So they both sum to identity. So this constitutes a valid measurement. Okay, so the high-level idea is that we'll use Y plus and AIs to construct a quantum protocol, similar to the classical protocol that we saw earlier. The protocol is essentially the same thing. So recall that for each x, because this is the spectral norm condition, you have yx. This is a quantum state because its trace is 1 and it's PSD, and Alice just sends a state across. So this is again the analog of the jth index, which witnessed that the spectral witnessed that the infinity norm was like larger than the quantity. The corresponding witness in the matrix case would be a PSD matrix. Does that make sense? There you could think of a witness as being a probability distribution because the dual norm to the infinity norm is the one norm here. The dual norm to the spectral norm is the trace norm. And all Bob does is just measures with respect to a plus minus 1. And for exactly the same reasons as before, you can show that the expected probability of Bob is half plus delta over n. Okay, that's good. So basically, what we saw is that vectors, if the Spencer's theorem were true, which we know it is, but if Spencer's theorem were true, if for all vectors v1 to vn, you had the discrepancy was small, using this connection between communication and discrepancy, we can show that there is no log n plus like constant bit protocol for the index function, such that the expected error is greater than half plus, say, 50 over root n. Does this make sense? So the first statement is Spencer's theorem. Basically, from what we saw, we can infer that this implies that there's no quantum, so there's no communication protocol for the index function. Does that make sense? Is everyone on board? At least at a high level. So the details maybe don't matter too much at this point. Okay. So cool. From what we went through a little bit fast, maybe, but from the same analogy, you can see that again the first line is the matrix Spencer conjecture, and through this communication and discrepancy connection, you can say that this follows from a by showing that there is no log n bit qubit protocol for the index function. This is actually very similar to the conjecture we saw earlier. But it's not, and I will maybe in a bit see why, what the difference is, and why we should care about the difference. Is everyone with me so far? Again, this is a good question, a good time to ask questions about what we just did about discrepancy and quantum, or discrepancy and sort of communication. And again, happy to answer any questions and go back in the slides if need be. Okay. Cool. I'll continue then. Okay. So what is the issue with this approach? The main issue is that it's not clear how to show these lower bounds because of sort of the questions like of average case for Bob. Furthermore, even in the classical case, the only way we really know how to show this is basically the proof of Spencer's theorem. So somehow this is not very useful. And also note that the error requirement is extremely close to half. So it's half plus like some delta over square root n. And this also makes it really difficult to show these theorems. So this is sort of like one reason why this approach, for this whole approach for thinking of discrepancy is sort of seems useless, like sort of to begin with, because it's not clear how to show the the standard techniques for sort of communication complexity lower bounds don't apply in this setting, at least immediately. Okay, cool. Okay, so are there any questions? I think we'll sort of in the next sort of few slides we'll see how to we'll move to a somewhat completely different maybe a somewhat completely different thing, and we'll see how to deal with these issues. So I just want to make sure that everyone gets what the issues are and what concern is. Okay, so okay, so one way to deal with this is somehow this notion of partial colorings. Partial coloring is something super simple. instead of looking for vectors in plus minus 1, the like integral plus minus 1, we look for vectors in the solid hypercube plus minus 1, but we insist that like a linear number of coordinates are actually integral. So such an object is called a partial coloring. So a standard technique in proving discrepancy bounds is usually first find a good partial coloring, then iterate on the instance by fixing the integral coordinates. And you get a smaller instance and you sort of iterate on this. This is how like most sort of algorithms for Spencer's theorem work. They mostly look for a good partial coloring and then continue. Turns out there's also sort of a big problem in showing many of the big conjectures in discrepancy theory. Somehow, like in at least those settings, partial coloring techniques are a little too wasteful. Right, and this somehow is like the standard way of constructing algorithms. The main so our main insight in our paper is that we can trade off average case Bob for average case Alice if we replace full colorings. Like in the previous setup, we saw that we had full colorings. We replace that with like partial colorings, and that's somehow how we get like tractable communication low bounds, which we can actually try to prove. Does that make sense? Okay, so here's a main lemma from our paper. Here's it formally stated. So let's say there are vectors in sorry, there are matrices A1 to AN, n cross n matrices, such that the spectral norm is bounded by 1. And let's say that there is no partial coloring that is omega square root n. This implies that there is a log n bit protocol for qubit protocol for the index function, such that the error guarantee now is a little different. This is expectation over x minimum over I. So before we had a minimum over x and expectation over I. So now we have average case Alice and worst case Bob. And the probability that Bob succeeds is the same. This is half plus c over root n. Right? Does this statement make sense? Cool. So basically what this tells us that if you can show communication low bounds in the average case Alice and worst case Bob setting, you can show that there are desired partial colorings. And furthermore, this lemma is actually algorithmic. Getting back to a question that Anand asked earlier, somehow this lemma also shows us that there is actually a very simple algorithm that recovers these partial colorings. The algorithm is actually, in some sense, it's actually trivial, which is there's a set of good vectors, and you take a random vector and solve the corresponding linear program in that direction, and you can show that this works. This algorithm gives you good partial colorings. So because we are the set of vectors we're looking at are like specified by matrices, this would be a random STP. So that's why this is sort of related to this is why you get algorithms out of this. This lemma somehow tells us that not only are there good partial colorings, they can actually be found by a super simple algorithmic procedure. Okay, does this make sense? So yeah, I think for most of the rest of the talk, we're not going to talk about discrepancy. We're just going to talk about
what
the
does
communication.
random SDP mean?
So okay, what does the random SDP mean? So here's the exact algorithm, maybe precisely. So let me try to write it. Yeah, let me. So can you see this? Okay. So you can ask for x which is a set of all vectors which have which satisfy this, right? These are all real valued vectors that satisfy this, right? This is a spectrahedron, like this is a feasible set of an STP. Do you agree?
Yes.
Yeah. Okay. Then what you do is you pick a random vector in plus minus 1 to the n, and then solve the linear program. Max of y, x in a product. Oh, I shouldn't use x. Maybe just I'll call this y. And max of z, z in a product x, for x in this set. Sorry, z like x is sorry. Oh, this is y and z in this set. Does that make sense? So you have this set of constraints. You take a random direction and just solve the STP in that direction. Solve the linear program in that direction. This is what I mean by random STP.
Sorry, why you took randomly from the set, is it?
Yeah. The objective I took randomly from the objectively I took randomly from plus minus 1 or a Gaussian. It doesn't matter actually what it is. Take okay, with the scale of it I guess matters. You take a let's say a random plus minus 1 vector, and then you can you hear me?
Yeah,
Yes. So why are we maximizing y in a product Z?
So that somehow goes into the analysis of why this works, but roughly the idea is somehow in this actually you need to take intersection.
Oh, so this is
with,
supposed to give you like a partial coloring with omega n
yeah
plus minus 1.
Yeah, exactly.
And I guess
Exactly.
anything
Because
in K is like a feasible partial coloring, and you're maximizing this to get like a boundary point or something.
Yeah, exactly. So every element in K is feasible coloring. But somehow you also need to take intersection with the hypercube, and the thing that needs to be shown is that this has many integral coordinates. That's the hard part of the analysis. So by definition, this gives you a good like it has low discrepancy. The issue, the hard part is showing that this has low. It has many integral coordinates.
So is this like, so can we view this as being something like a matrix analog of this Lovett-Maker algorithm?
It's actually very similar to, okay, it is a matrix, it's exactly a matrix analog of Eldon-Singh, if you have seen that. But it's, okay, it's very, okay, all these algorithms are very related, as in their analysis sort of work the same way. But the closest conceptual relatives to this algorithm are the Rothfuss's algorithm for rounding, like Rothfuss's algorithm for discrepancy, and Eldon-Singh's algorithm for discrepancy. They're most closely related to this algorithm. Lovett-Maker is also like sort of is very related, but it's not exactly the same thing.
Right. No, so I mean, given this is the linear program or SDP that you're trying to solve. So I'm just wondering if something like Lovett-Maker would also work here. Like you started a feasible X and then do a random walk, and then if you hit an integer point, you fix that coordinate and then continue your random walk.
That's a good question. I mean, again, the hard part in Lovett-Maker also somehow is to show that you hit many integral coordinates. Like in all the analysis, the hard part is showing that there are many integral coordinates, integral constraints that are hit.
Yes, but I guess this lemma is doing that part anyway, right?
Yeah, it's not
Oh, it's
okay.
only
It's not
showing the
immediately
edges. You
obvious.
still have to find it. Okay.
Yeah, it's not obvious that Loettmacher's algorithm would like find the colorings. It's actually a good question. If it follows from this analysis, if Loettmacher's algorithm finds it, it's not immediately clear to me. But I think it's plausible. Does that make sense?
Okay. Yeah. Thank you. Yeah.
Yeah. Is the partial coloring here also like the almost integral one, or are you taking completely integral? Like in the lower.
So we find yeah, it's very similar to Loettmacher, like n over 2 coordinates that are integral. Somehow not restricting, not having let's say a linear number of coordinates integral is sort of not very useful because 0 is a low discrepancy vector, so you need some integrality constraint. And like these algorithms somehow struggle to find all coordinates that are integral directly in one step somehow. So what we show and even Loettmacher shows that let's say n over 2 coordinates are integral.
Don't they assume one almost integral, like 1 minus delta thing? N over 2 indices are almost integral, or maybe I'm mistaken.
Oh, sure. Okay. Okay. Now that gets into the issue of numerical. I mean, how do you sort of actually deal with um, uh, how do you actually deal with, like, I mean, you have to solve an STP. Okay, if you actually run this algorithm, you'll only approximately solve an STP, right? So you're not gonna actual corner point, you're gonna get a nearby corner point. So in that sense, you're gonna be almost integral, but like same sort of general high level ideas are gonna, you can just round to the nearest thing and it's gonna work.
Okay.
Does that make sense?
Yeah, thanks.
At some level, it's a numerical precision issue. Cool. Yeah, thanks again for the questions. So okay, so let's in how much time do I have left?
Well, I think we can go for a few minutes.
Okay, I'll just sort of quickly talk about like the communication complexity of the index, and then hopefully just sort of try to convince you why this is interesting and why this is sort of okay. So the randomized communication complexity of the index function is omega n if you have advantage that is a constant. And the quantum one also you can show is omega n if you have advantage constant. This is also known as quantum random access codes. The proof usually uses like information theory and sort of Holevo or the quantum analogous to Holevo bounds. Unfortunately, for discrepancy, we are in the low advantage setting, and the bounds using information theory sort of break down because the binary entropy near half is approximately like 1 minus epsilon squared, and because of this, you get if you set epsilon to be 1 over root n, this gives you sort of a quadratic ish bound. That's like you get a constant bound rather, because if epsilon is 1 over root n, you get 1 over n, but like you multiply this by n, that's going to give you a constant bound on the communication complexity. So it's not super interesting.
What are these Holevo bounds? Are these some sort of concentration inequalities? What is this?
The Holevo bound is at a high level. It says how many qubits do you need to send to faithfully convey n bits of information. And turns out the answer is n, and that's what Holevo bounds show you. If you wanted to actually faithfully convey all n bits of information in even using quantum messages, Answer is n. This at face value might be a bit surprising, but it makes sense. That's what our Holevo bounds are.
Okay.
Does that make sense? So if you don't have too much time, maybe it's not valuable sort of going into the proof of what I was going to do next is like a proof. So if we want to sort of end like soonish, maybe we can I can skip the proof. But if we have some time, about like 5-10 minutes, I can just go into a proof of the again communication complexity of index, and we'll just talk about like one proof technique that flows out of this. How we show sort of the wider communication complexity. What do you guys think?
I think we can do 5-10 minutes more.
Okay, sounds good. So this is sort of interesting. Okay, so one other interesting comment that is worth making here is that in the unbounded error regime, there is actually a quantum advantage over the classical protocol. So in the above thing, it doesn't seem like there's a quantum advantage. What is unbounded error communication complexity? It is you are asked to predict the answer just with probability strictly greater than half. It does not matter how much greater than half it is, as long as it is strictly greater than half. Half is the you can get half by guessing, so you just have to have error better than half, right? And in the classical setting here is log n bits, and the quantum analog of this is turns out to require half log n bits. And that's somehow the problem. We'll get to that a bit later. Okay, so this is a conjecture that we saw earlier. So let's try to prove the conjecture in the classical case. So we want to show what the communication complexity of the index function is when you have half plus 1 c over square root n error, right? And we want to show that this is at least log n bits. Can anyone tell me what a natural way to sort of approach this is, given that we know how to do this for, say, the constant error regime? Right. Okay. So like a really natural thing to do is just boost the advantage by repeating the protocol many times. So what Alice can do is just send Bob many copies of what she would have sent in, like independent copies of what she would have sent in her protocol, and then Bob just sort of um, takes advantage of this, right? And then you can take a majority vote of all the answers that Bob would have given and given the answer. So this gives you sort of a boosted probability of error. Is everyone convinced that this at least vaguely works? Can anyone tell me what the issue is? Why this doesn't like sort of naively work? So yeah, the main issue is that if you have advantage that is like half plus epsilon, like if your advantage epsilon, that is your error is like half plus epsilon, you approximately 1 over epsilon, I think 1 over epsilon square repetitions. Therefore, you get like a 1 over epsilon square times log n bit protocol for the index function. But you had epsilon is 1 over root n. So this tells you that you have an n log n bit protocol for index function, which is not a contradiction. Does that make sense? So this does not give us a lower bound. This So you can't take a log n bit protocol for the index function and just boost the error to get a good protocol for the too good to be true protocol for the index function with constant error. Does this make sense? Is everyone does that make sense?
Yeah.
Okay. So how do we get around this? The main observation is that somehow the only thing that Bob needs to do is take a majority vote, and the majority vote is a symmetric function. So somehow the order of the messages that Alice actually would have sent is not important. So the hope is that you can compress the protocol even further after repeating it. So because you just need to send you don't need again the order. You can only send the histogram of the messages. Because the protocol is a log n bit protocol, the possibilities is n, and there are 1 over epsilon square of these many messages. The number of possibilities is approximately n choose 1 over epsilon squared, and this is log of this is clearly less than n. So Alice only has to send order of n bits n bits, which leads to a contradiction to the full error, so constant error communication complexity of the index function. Does that make sense? So basically, this gives you this itself is along with the earlier discussion about communication and partial colorings and discrepancy, it gives you another proof of Spencer's theorem. Okay, so let's very quickly see how to do. So what we can show is that this actually works out in the quantum case as well. But if Alice is forced to send only pure state qubits, as in instead of mixed states, she can only send pure states. And the proof is actually essentially the same because it's a symmetric. The symmetry observation is still true, and instead of you take the quantum analog of the symmetric thing, which is the symmetric subspace. So it's not super important. But unfortunately, this does not suffice for the matrix Spencer conjecture. Uh,
What are these?
but it actually
qubits? Sorry.
So yeah, pure state. Okay, so in quantum mechanics, I told you that the state is represented by this matrix, which is whose trace is 1, right? You should think of this as probability distributions. The quantum analog of probability distributions. If that row was rank 1, it's this thing is called a pure state, which is the analog of a probability distribution which puts all its mass on, say, one element. So it's the analog of not having sort of I mean, at a high level, you should think of a mixed state as classical randomness over quantum states, and somehow a pure state is something that has no additional classical randomness on top of the quantumness. So it's just a pure quantum. It's a quantum analog of a deterministic thing. Well, which it's again not the correct way to think of this because quantum things are inherently probabilistic, but that's an aside. So it's does that make sense?
Yeah.
So that's what a pure state is. If you're thinking of communication complexity, this is the same as saying Alice is not allowed to have private randomness. This is something super weird, and we don't I don't fully understand it. At least we know how to show a lower bound when Alice is allowed randomness, and Alice is just allowed quantumness, but we don't know how to show a lower bound when Alice is allowed randomness and quantumness. Just super weird. Yeah, so it turns out this lower bound is not enough for the matrix Spencer conjecture. It turns out it's enough for the moderate rank matrix conjecture, but the proof of this is a bit technical, and maybe it's not worth it to go over it in a rushed way, because it. So I'll just skip the proof of this and basically go to the conclusions. The main question which the main question which remains, I guess, is matrix Spencer conjecture true? And even if it is not, I think we can construct interesting objects in communication complexity, even if there was a counterexample. So either way, it is interesting, and that's sort of at least tells us there's some good reason to study this problem. In addition to that, there's like connections between quantum information and non-commutative discrepancy has been like there have been other instances where this has come up. Like one big example of this is the Cadison-Singer problem. One could even optimistically ask if some techniques like this would be helpful for the Cadison, like algorithmizing Cadison-Singer problem, but that is being unnecessarily optimistic, I think. But it's still good to sort of understand. And as before, like one thing to ask is if there are any other applications to other problems and discrepancy, and if this sort of communication view can be helpful in other settings. Thank you. That's all I had to say. Happy to answer any questions, or again look at any other. We can go back to slides if there are any questions. Thanks so much. Thanks.
Great talk, Abhishek. And one question. So this SDP that you said, you pick a random direction and you try to maximize along that, and you think that finds a feasible partial coloring. So since you're picking a random direction and it's kind of finding partial coloring, does this suggest that there are actually many partial colorings, not just one?
Yeah, that's a good question. I think it suggests that there are many good. Okay, so this is actually a great question. So we can show that it's actually easy to see there are not many good full colorings, because you can show that the sort of the probability of this is like exponentially small. So it's certainly true that the full colorings are like a super small set. But yes, it is true that like somehow these techniques show that the partial colorings are like somewhat common. But on that note, somehow the main difficulty with this technique of partial coloring, even though they're like very common, is somehow it seems like we don't know how to analyze, for example, what indices are partially colored. Does that make sense? Like
sorry, what does that mean?
they're super. Okay. You pick a random direction and you get some partial coloring, which is all good. It's a good partial coloring. If it's a good partial coloring, if like n/2 of the indices are like integrally colored, right? Like I was telling you, sort of the algorithmic idea for the next steps is going to be you're going to sort of fix those indices and going to iterate the problem on the second half. Now it would be really good if I can tell something about what the second half, like I'm iterating on, is like other than just like saying it's a smaller instance. It sort of would be useful to be able to say some like sort of random, like you notice, because this is a random SDP. This object should be sort of super random, but we just don't know how to actually say anything about it. Does that make sense?
Yes.
So in one sense, like somehow, yeah, in some sense, like it just like there are many good partial colorings, but like we don't actually know how to deal with the randomness that gives us. Yeah, and sort of many sort of big open problems, like 50-year-old open problems in discrepancy is sort of would be sort of maybe you can make progress on it if we can somehow understand the probabilities of these partial colorings well, because for many of these problems, for example, Komlow's conjecture, we know how to find good partial colorings. This like it just follows from say Lovett maker. The problem is we don't know how to iterate on it without taking too much loss. Because again, somehow essentially we have to pay sort of worst case loss, because even though these partial colorings are like random, we can essentially say nothing about them other than that they're good and they're partial colorings. They're good as in they have good discrepancy and they're partial. Yeah.
So, are there any other questions? Okay. In that case, let us thank the speaker, and I'll stop the recording.